Okay, let's get started in chapter 26, current and resistance. Before we get started, let's just ask, what is current? Seems like a pretty good way to start a discussion about it. And so we kind of have the definition that current is the flow of charge. Right, we had our I is equal to dq dt. Where one way to think about that is if you have some plate full of positive charge and you add a conductor such that as time dwindles on, maybe you lose a couple of these charges as they flow through this conductor. You can find a delta Q for how much charge left, a delta T for how long it took, and then I is equal to delta Q over delta T, right? Which should make sense because the more charge you leave and the faster it happens, the greater your current, right? If all of these charges hop off very, very fast, you have a very high current, right? And that's the idea. One thing we should keep in mind is that pretty much any circuit we deal with, let's say we have some potential, right, from a battery, and then let's just say this goes on to a resistor, right, we almost always use what's known as a conventional current, which is the flow of positive charge. Right, and so we could look at this circuit and say positive charges leave the positive plate of the battery and flow through this circuit clockwise. Is that how clocks work? Yeah. Right, but we know. Ooh, that was an aggressive line. That's still pretty aggressive, cutting through the words. Right, there we go. But we know typically it's going to be an electron current. Which is the flow of electrons. Right, and so we know in reality when you have a battery, it's actually the negative charges that are going to flow anti-clockwise. Right, and that's because Benjamin Franklin's a jerk. But it's mathematically easier to deal with a bunch of positive charges than it is to deal with the negatives, right? If we always dealt with an electron current, we would just have minus signs everywhere, and it just is not fun or useful to deal with, right? And so if you have negative charges flowing counterclockwise, that's mathematically the same as positive charges flowing clockwise. And so this works. We can get away with this. Right. And then just from our equation that we came up with for current, we can also say Q is the integral of dq, right? Just by definition of an integral. Which we can then say is the integral from 0 to t of I dt. And you can figure out how much charge is left in area. So let's start coming up with a picture, a little microscopic image of what's going on in any kind of conducting material, typically a metal. And so if we have a bunch of positive nuclei in here, and a bunch of negative charges that are kind of free to move around, right? If this is, in equilibrium, we're not doing anything fancy in here. Like, it's just we're hanging out. There's no external electric field. There's no potential difference, right? kind of the same thing. Right, we would expect if we pick directions for these charges to move in. Actually, let me kind of set this up to be a bit nicer for me. We'll do one there, and one there. Yeah. If we take some arbitrary cross-section, I say arbitrary even though I very clearly just cooked the books, but it will be okay. And say maybe this charge is going this way, this one's going that way, this one we can have going this way, maybe this one's going this way. If we look at delta Q for either side of this boundary, we see it's equal to 0, right? Because we had +1, +2, -1, -2, right? There's no net charge flowing. And this is true for all conductors at equilibrium, right? And now I drew 4 charges here. It's typically closer to like billions, or many billions per second. But delta Q is 0 because there's no net transfer of charge, just because there's no incentivization for the charge to want to flow either way, right? You come along and you add an electric field or a potential difference, and that's known as a bias, right? You're incentivizing the charge to flow in one direction or the other, and you get a net current. All right, and so in general, if we were to look at any of these electrons and what they're doing, they're kind of, well, we'll get into that a bit more. What we want to note for right now is they have a speed known as the Fermi speed, named after Enrico Fermi, and it's approximately 10 to the 6 meters per second. Right, which is 1% the speed of light in a vacuum. Right, so they're going fast. Right, but they're just constantly bouncing around, not really doing anything if there's no incentive for them to do so. Okay, so let's talk about the units for current. If we have I is equal to dq dt, we have the unit amps, which is going to be charge per time. More specifically, 1 amp is equal to 1 coulomb in 1 second. Right? Which, if you keep in mind, an electron is 1.6 times 10 to the negative 19 coulombs. Right, when you have a current of an amp, that's a lot of electrons moving around, like a staggering amount, and very fast to get that many in a second. And that's what we actually deal with in the real world. And so when you get to values this high, you no longer really have to worry about the quantization of charge, just because you are dealing with such great quantities that individual electrons no longer seem to matter. If you have something where you're dealing with, right, you could easily have a current. Let's say you have an atom, right, some large atom, right, and so you have some nucleus, right, it's neutral, so, you know, you can count up how many ever electrons I drew and figure that out. And if you were to have some method of ionizing this atom, you know, whether it's a very strong external electric field, you know, various things can do that. And so if you start knocking off atoms, all right, now maybe they're all shooting away this way, you could find delta Q and delta T and find a current in which you need to make sure charge is still quantized, right? It has to be a certain amount of electrons per second. But when you're dealing with quantities this big, you know, you're dealing with 10 to the 19-ish electrons, and so 1 doesn't really matter. Okay. Another thing we need to keep in mind is conservation of current, which is kind of an extension of conservation of charge, if you think about it. And so let's say we have some kind of a wiring setup with a junction in it, and we know it has some current I0 flowing into this junction. Well, if we have I1 and I2 flowing out, we must make sure that I naught is equal to I1 plus I2. And if we had some circumstance where maybe I2 is greater than I naught, then the only way for that to be possible is if I1 is also flowing into the junction, right? And so then, we could make this say I naught plus I1 is equal to I2. And what would essentially happen is if you solve for these currents in this equation, you would get I1 is negative, right? To show that it has to flip directions, right? And so that's saying that if you started out with it going this way, you would find that you get a negative result, which corresponds to it just flowing the other way. Okay. So let's do checkpoint 1 from the textbook real quick. Which I highly encourage you to do these checkpoints as you're reading. They are like really good. Just make sure you know what's going on. And so I'm just gonna draw the setup. That goes there, nothing there. We go boom, boop, boop. And we're given 2 amps goes this way, 3 amps this way, 4 amps going up here, 2 amps flowing that way, 1 amp, 2 amps. And then we want to know what the current is down here. And I think that's all we're given. And so, right, you can start, in a couple different spots, but I'm going to start by looking at this junction here. If we have 2 amps going in and 3 amps going in, we need 5 amps going out, right? Just so that there's the net current at that junction is 0, right? It's not a sink, it's not a source, it's just kind of a pathway for things to flow through. And so then we know we have 5 amps flowing into this junction. And so we can figure out what flows out in each direction. So if we look, we have 2 amps going this way, 1 amp going this way. That means 3 amps must be going into this junction. And so this leg right here must have 3 amps going up through it. And then if we have 5 amps going into this junction, 3 amps leaving upwards, that means 2 amps have to go down. Okay? And so then we get to the next junction. And we see we have 2 amps going into it, 4 amps going into it. So that must mean we have 6 amps leaving that junction. Then we get to the final junction where there's 6 amps going in, 2 amps going in. And so we must have 8 amps going out of that junction. And that'll be the answer. Okay. So that's cool beans. And so let's hop on to 26.3. Current density. Okay. And so we kind of want to start thinking about current as a flow. Right? And so not always necessarily thinking about the individual electrons and what they're doing, but we can kind of think about just like a flow, like a stream of sorts. And so to do that, we come up with some variable called a current density, J, which is a vector. And so this is going to have the same direction as the velocity of charges. I'll just put charge. If the charge is positive. And opposite direction if negative. Right, and because again we're just talking conventional currents. And so this current density, we can say J has units of charge per area. And so we can say current is equal to J times A. But we can be a bit better. We can say it's equal to J dot dA, right? And so we're kind of starting to think of current as a flux of charge. Right, which should kind of make sense from what we were doing up here, where we picked some random cross-section area and figured out how much charge goes through that area, just like we were doing with electric fields. Right, and so we had electric flux is equal to the integral E dot dA. And then let's see, what did we do? We said E was parallel to dA, and so then we had the flux is equal to E dA, and then we said E is constant, and so then we had this is equal to E times the integral dA. I guess we can do that. That doesn't, we can kind of lose the circle if we're losing the dot product, I guess. And then we can say, well, this is just equal to EA. So what we're going to do here is we're going to say we're going to choose our cross-section so the J is parallel to dA, and then we get I is equal to the integral of J dA, and then we're also going to have J is constant. And so we have I is equal to J dA is equal to JA. It's a jacked up J. Okay. And so if we have I is equal to JA, then we can say J is equal to I over A. All right. Just ways we can start messing with these things. Cool. And so we'll put a box around that because that's going to come in handy a bit later. And so let's start talking about drift speed. Right, so we discussed the conduction electrons bounce around at Fermi speed. Which is wicked fast. But we're going to find that conduction electrons actually travel at a very low speed, right? And so let's kind of come up with a good picture we can have in our head. And so we're going to go back to this conductor. That'll do. And then we're just going to look at like one electron. And so essentially, if there's no incentivization for the charge to go in a specific direction, right? And so that can either be done through potential differences or electric fields, which kind of the same thing. Well, they're related, right? You need one to have the other. If there's one, the other exists. So you know, all right. Those are what would incentivize a charge to pick a direction and travel in it, right? But in here, you could, you know, if you want to see what this electron's going to do, right? Maybe it hits one of these atoms, and then every time it does, it picks a random direction to travel in. And so maybe it zips over here, and then it goes boom, 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 and it's like a pinball machine. Cool. Right, just bouncing around randomly, not really getting anywhere. And so let's consider a similar picture. Well, we can probably just extend this a bit. Don't have to scroll down too far. No, we're gonna erase this for now. And so now let's go ahead and say, ooh, I want these to be negative. It'll make my life better. Negative, 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 negative. Didn't need to do that. And then we'll come over here and do positive, 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 positive. And then we'll go back to, we have our nuclei, and we have our electron. Well, we know F equals QE, right? We know this is, excuse me. We're going to have some electric field going this way. And so our electron's going to experience a force to the right. It's going to want to go towards the positive or against the electric field. And so we know there's always going to be some force to the right on this particle. It's still zipping around at its Fermi speed. And it's still making all these collisions. And now it's going to bounce off in a nearly random direction, right? What we drew previously, that was a fully random direction. And now we're going to do a nearly random direction. And so we can have maybe our electron scatters, and it's always going to kind of be incentivized to go to the right. And so maybe it hits down here, goes up here, right? It can still go to the left, but it's just more often than not, it's going to travel to the right. And so if you let this happen long enough, right, this electron is eventually going to make its way down to the end, right? But it's just going to take a while. And that's known as the drift speed. Right, so if we were to maybe draw the path that this would take in the absence of an electric field, maybe it goes up here, and then it comes down here, and it goes back here. And so it's just going to be slightly off, right? Right, and so if we look at the two electrons, maybe the one that's drifting ends up right here. The one that isn't drifting ends up over here, over the same journey. And so it's not a huge difference, right? It's just going to kind of coast a little bit to the right from every interaction, right? Nothing too drastic. It's not going to fully change the direction. It's still semi-randomized, but it's just influenced to go in one direction now, right? And that's drift speed. And let's see. And drift speed, we get velocities of 10 to the negative 4 meters per second. Some sources are going to say 10 to the negative 5 meters per second. Right? And so I think if we're bouncing around at 10 to the positive 6 and we're actually drifting at 10 to the negative 4, right, that's crazy slow. Okay. And so let's kind of go along with how the book tackles this topic briefly. And so the book says we have some conductor. We're going to look at some length L. We have some amount of positive charges. And I think the book's going to have the positive charges traveling. Yeah. And so we have some net electric field going this way. So we know the force is going to go that way. And we know the current's going to go that way. And so if we go ahead and say we have some amount of charge per volume, N, right? That's the number of charges per volume. And then if we go ahead and say this has a cross-section area A, then we can say the total charge we have is equal to N times A times L, right? A times L is the volume, right? And so this is the number of charges per volume. And if we multiply that by E, right, if we say these are all protons, then we get the total charge, okay? And it says all of these charges are going to travel with some drift velocity, VD, which here we go, might as well put VD. Right, ain't that pretty. Okay. So then the total charge moves through any cross-section of the wire in this time interval, right? And so the amount of time it's going to take to travel some distance L, well, we know time is equal to what? Distance over velocity. So we can say L over VD is the amount of time it'll take. And then if we have our equation, I is equal to, we have dq over t, or delta q over delta t, dq dt. We're just going to say it's equal to q over t. If, q is the total charge, t is the total time. So what can we say about that? Is NAL times E for the total charge. Let's kind of move this down a bit. And then we said T was going to be L over the drift velocity. So we can go ahead and cancel these out. And so we get NAE times VD is our current. Okay. And then if we know J is equal to I over A, let's see, what can we do then? Well, let's start by rewriting this for VD. All right, so we're going to start with I is equal to NAE VD, which turns into the drift velocity is equal to I over NAE. We have J as I over A. We have an I over A right here. And so we can say the drift velocity is equal to J over NE. Okay. Or if we want the current density, we can say J is equal to NE times VD. And so what's this tell us? Our current density, current per area, is equal to the number of charges per volume times E is the charge times the drift velocity. Right? And so this should make sense, right? The more free charges per volume and the faster the drift velocity, the greater the current. Cool. But I still think this idea here is very, very nice to think about when talking about Fermi speeds and drift velocities. All right? And so then we would say maybe the amount of time it took a charge to get from here to here is the drift velocity, is the speed at which it did that, right? Versus the Fermi speed, which is how fast it's bouncing around. Okay, so let's go to 26-4, resistance and resistivity. Okay. And so let's start with Ohm's law real quick. V equals IR. Right, and so that's, if you apply some voltage to a circuit, you get some current through that circuit, and it depends on the resistance of the circuit. And so we actually use this as our definition of R. Yeah, so R is V over I. And this is definition of resistance. Okay, and so this R equals V over I, right? If we think about it, it's just says, right, if you have some V, whatever's going on, and you get some resulting current, the ratio of that potential to that current gives you R, the resistance of the circuit, right? So it's kind of similar to how capacitance is like a geometric phenomena, right? So is resistance almost, right? It's like the geometry of the circuit nearly, right? If you give a certain push, the amount of charge that moves for that push is dependent on the amount of resistance in the circuit, right? And so this has to do with extrinsic properties, right? Just like capacitance did, right? You could very easily change any of these things and you would change the resistance you get, right? Well, not quite. But if you were to change things about the resistor, you would change its resistance. Not the most profound statement, but you'll see where I'm going hopefully in a second. Right, and so this all has to do with extrinsic properties of the circuit, but we can talk about something called resistivity. And this is an intrinsic property of the material. Okay, and so the definition of rho, it's equal to E over J, right? The electric field and current density, right? And so, right, we know potential is related to the electric field, and the current density, well, I guess maybe this would have made more sense. And current density is related to the current, right? If you apply an electric field, depending on how far the separation in the things for the electric field, or if it's two plates, you can change the potential difference. And then similar with current density, if you have a bias for charge to flow, depending on the area through which you let that charge flow, you can get a different current and current density. Okay. And so what we can do with this equation is we can rewrite it pretty easily as E equals rho J, with these being vectors. And then we can come along with the conductivity, which is equal to 1 over the resistivity. And we can say J is equal to sigma E. And there we go. So that's all fine. And like resistivity and conductivity, right? These are intrinsic properties of a material. You can look this up in a table. Right? And so they have a table in the book that, it'll go through and it'll say like silver, right? Ag is 1.62 times 10 to the negative 8th in ohm meters. And it'll go through and it'll list a bunch of materials in a table, right? So resistivity is intrinsic to the material. Resistance, though, that's going to depend on extrinsic properties, right? You can't just say, oh, silver has a resistance of this. because it's going to depend on the shape of the resistor you make, but its resistivity does not. Okay. And so let's calculate resistance from resistivity. And so let's see. We know resistance is going to depend on the resistivity. And then everything else is going to be the geometry of the system, right? And so that's going to be related to the length of the resistor and the area, right? Just like for a capacitor, we have C is equal to epsilon naught area over D. We're going to have something pretty similar for resistance. Okay, where resistivity is going to be our scaling constant, just like epsilon naught was. And so the way I like to think about this is, imagine you're trying to drink some boba tea, I guess is a good example. And so you trying to drink, like the suction you provide is similar to the potential, right? It's what is incentivizing the boba, instead of like the charges, to flow. And so the harder you try to drink, the more boba you expect to flow through the straw given a rate of time. So flow of boba is going to be flow of charge, and I hate that I have to write this. This is a terrible metaphor. And sucking is going to be like the potential difference. Which, if you think about it, when like a vacuum cleaner sucks on something, it is lowering the pressure inside of itself compared to air pressure. So it is like a gradient of pressure versus a gradient of potential that makes things move around. So this is actually a decent metaphor. Right. And so what's going to determine how much boba you get based on the straw, right? And so you have a straw, I don't know, boba, and then you got all the little tapioca pearls at the bottom. And so let's think. The longer the straw is, the more difficult this is going to be, right? The greater a distance you have to transport these boba pearls, right? And so we can say it's rho, and then let's see. So we're going to put 1 over L, right? Because if this straw were to be, way out of here, then you're going to be there all day. You're not going to have a good time. The restaurant's going to close. So there's that. What else can we think about? Maybe the cross-sectional area of the straw. Right, if we had maybe you took like one of those little coffee stirrer straws and tried to do this, right, you'd be there all day, right? And so that's a higher resistance, right? And so, oh, wait, did I mess this up? I did. Right, resistance is difficulty, so the longer it is, the more difficult it is. So we need the A over here. Right, and then so area, the greater the area, right, the wider the straw is, the more tapioca pearls you can fit in there. And so the bigger the straw is, the lower the resistance. And so you get R is equal to rho L over A. Okay? Right, and so just, think about trying to drink some boba tea. If the straw was really long, you have a very high resistance. It's very difficult. If the area is very small, also you have a very high resistance. Okay. So we have that. And then let's talk about variations of resistance with temperature. Okay. And so for many materials, as temperature increases, resistance increases. Right? And this is, I want to say, kind of counterintuitive to a lot of students. Right? Because they want to think like, oh, if I have, I don't know, like a jar of maple syrup, if I heat it up, it flows easier. Right? But that's not what we're dealing with here. Right? We're not talking about how easy it is to make charges flow like a liquid. We're talking about the barriers to letting them flow based on the material parameters is resistance. And so the way I like to think about this is, right, think about kind of you're at a concert, right? And so maybe the first concert has a mosh pit. Maybe the second one's ballroom dancing. Right. And so I don't know if many of y'all have been to many mosh pits or ballroom dances. But let's say the positive nuclei in the material are the moshers or, you know, the ballroom dancers. Right. And so in a mosh pit, right, they're all kind of slamming around, bouncing into each other, doing all sorts of crazy things. In ballroom dancing, they're just kind of swaying back and forward. Well, imagine you're trying to walk through either of these events, right? You're just a young electron trying to cross through this, right? As you try to get through the mosh pit and everyone's kind of pushing and shoving, you're going to get kind of jumbled into the mix, right? And so that's like a high resistance event, right? It's going to be hard to walk through all of these people kind of, you know, crammed together, pushing, shoving, you know, having a good time. Versus if there's ballroom dancing going on, you can just kind of cut through very easily. And so that would be considered like a low resistance. All right, and if I were to ask you which event had a higher temperature, right, mosh pits or ballroom dancing, you'd probably agree that a mosh pit is a much higher temperature event than ballroom dancing. And so while it's not exactly the same thing, right, there's not actually pairs of nuclei swaying together, but if you're looking at some kind of a conductor at low temperature, right, they're just kind of wiggling a bit in all directions. Unless you're at absolute zero, in which case everything stands still. Right, and so you can imagine, right, if you are an electron trying to go through there, it's not too bad, right? You can just kind of cruise through. Versus high temperature, now everything's very violently wiggling, right? It's shaking all over the place. You have a lot of vibrations. And so you can imagine if you're an electron, you're going to get smacked by this atom, then maybe smacked by that one, then smacked by this again, and you're just going to get shoved all over the place. And so we have high resistance at high temperature, low resistance at low temperature. And we have an equation, rho minus rho naught is equal to rho naught times alpha T minus T naught, right? So this talks about the resistivity and its dependence on temperature, right? And so oftentimes T naught is going to be room temperature, and so then your rho naughts will be resistivity at room temperature. And so then if you're at some elevated temperature T, you can find the resistivity, and then you can find the resistance using this. Cool. And so this is why, like, let me think here. Right, if you think of an incandescent light bulb, right, which has a tungsten filament, right? I guess maybe there's another little leg coming down that you flow current through. The whole idea there is, as you're flowing currents through, you actually heat up that element, and you eventually get it hot enough that it incandesces, right? It starts emitting light. And so if you were to measure the resistance of that filament as a function of current, you would find it doesn't follow Ohm's law. Right, because as it heats up, so does its resistance, right? And so, which then causes it to heat up more, and it's, it's a great cycle that, makes things light up very well. Okay. And I think we can probably, oh, no, let's go to 26.9. Power in electric circuits. And let's see. So we had said that U is equal to QV. If we take an infinitesimal, we could say DU is equal to dq times V, right? If a battery just has a known potential. We can say dq is equal to I dt. Okay, and so we have a expression here. If we move the dt to the other side, we would get du dt is equal to IV. Well, du dt is the rate of change of energy, which we can call power. And so from this we get P is equal to IV. And so this is the rate of electrical energy transfer. And let's check the units real quick. So we have I, which is amps, V, which is volt. Let's see, a volt is joules per coulomb. An amp is coulombs per second. And so we get joules per second, which is watts. All right, and so the units work out that is power. All right, and then if we have V equals IR, and we want to work with P equals IV, you can go ahead and substitute in, let's see, what can you do? Well, V equals IR, and so then you get P is equal to I times IR, I squared R, or if you want, you can substitute in I is equal to V over R for I, and you get P is equal to V squared over R. And so we have these three equations here to talk about the power of a circuit. And so this P equals IV equation applies to electrical energy transfers of all kinds, right? This is the general case. where P equals I squared R and P equals V squared over R, these two here apply to the transfer of electrical, sorry, my dog's going crazy. Simmer down. Electrical potential energy to thermal energy in a device with resistance. All right, and so P equals IV is any type of electrical energy transfer. Okay. And I think we can wrap this one up